So calculation of system noise temperature. Frequently, when the RF amplifier in the receiver front end has a high gain, the noise contribution of the IF amplifier and the later stages can be ignored, and the system noise temperature is simply the sum of the antenna noise temperature and the LNA noise temperature. So TS equal to T antenna plus T LNA. So values for component gain in the final equation must be linear ratios, not in the decibel. So whatever we have determined in the equation of equivalent noise temperature, all those right hand side expressions must be in the ratio scale, linear scale, not in the decibel. If decibel is given, you have to convert it back to the ratio scale. Suppose some power is given, some gain is given, some say 10 dB gain is given. So you have to convert it into ratio scale. Then you can use it in the equation. The noise model that we have shown replaces all the individual sources of noise in the receiver by a single noise source at the receiver input. This assumes that all the noise comes in from the antenna or is internally generated in the receiver. That is quite obvious. Let us have a numerical example of related to system noise temperature. Suppose we have a 4 GHz receiver with noise temperature and gain like this. Okay, calculate the system noise temperature assuming that the mixer has a gain of 0 dB. Recalculate the system noise temperature when the mixer has a gain of 10 dB loss. How can the noise temperature of the receiver be minimized when the mixer has a loss of 10 dB? The system noise temperature can be written as that we have already derived, but keeping in mind we cannot use any term in this expression in decibel. If something is given in decibel, we have to convert it back to normal scale, right? For example, this 23 dB, 23 dB or 30 dB, all these terms must be converted into ratio. Okay, otherwise we cannot use it. If the mixer had a loss, as is usually in the case, the effect of IF amplifier would be greater. For GM equal to minus 10. Why minus 10? Because it is a loss. That is why minus. The linear value of GM will be 0.1. In ratio, it will be 0.1. So putting the value, you will get this expression. So previously it was 87.5 Kelvin. Now it becomes 137.5 Kelvin. The lowest system noise temperature are obtained by using high gain LNA. So we increase the LNA gain, say up to 50 dB. So 50 dB means it becomes 10 to the power 5 in the ratio scale. So if you calculate the equivalent noise temperature, it becomes 75.1 Kelvin. Okay. So just by increasing the gain, you can reduce the equivalent noise temperature, right? So high gain of LNA has made the system noise temperature almost as low as it can go. Ts equal to T in plus RF, that is 75 Kelvin, right? So LNAs for use in satellite receivers usually have gain around 40 to 55 dB for practical purpose. Noise figure and noise temperature. Actually, noise temperature is a way of representing the available noise power out of a particular component. Same thing is done with the help of noise figure. Okay, so it is noise figure and noise temperature are basically representing the same noise power with the help of two different way. Okay, so noise figure can be defined in this way. It is the available signal to noise ratio at the input side to the signal to noise ratio at the output side. So Noise temperature is more useful in satellite communication system. It is the best to convert noise figure to noise temperature. Using this relation, TD is the noise temperature, equal to T0 into noise figure minus 1. So if something is given in terms of noise figure, you can easily convert it into noise temperature and vice versa using this uh, expression. This noise temperature in a linear ratio, again mind it, we cannot use any decibel value right here. So if some decibel value is given, you have to convert it into ratio scale, mind it. And T0 is the reference temperature. Generally it is taken as room temperature or 290 Kelvin. Generally noise figure is given in terms of decibel, but when you use it in this equation, in this expression, you have to convert it into ratio scale. Let us have an example. Noise figure is given as 2.5 dB. What should be the equivalent noise temperature? So TD equal to 290 into 1.78 minus 1. So if you convert this 2.5, it becomes 1.78. Okay, this is in decibel, this is in the normal ratio scale. So it becomes 226 Kelvin. Okay, the link equation can be rewritten in terms of C by N ratio at the R station, right? So C by N, that can be written as PTGTGR divided by KTSBN into lambda by 4 pi R whole square, right? Now let us take this GR and TS out. So PTGT by K into BN, lambda by 4 pi R whole square into GR by TS. So GR is the gain of the receiving antenna, TS is the noise temperature, right? All these other terms are actually constant for a particular system. Okay, so we can see that C by N and this GR by TS, rather G by T, they are proportional to each other. Okay, so the terms in the bracket all are all constant for a given satellite system. So GR by TS, which is usually quoted as simply G by T, can be used to specify the quality of the receiving earth station or a satellite receiving system, since increasing G by T increases the receiver's C by N ratio. C by N ratio, we have already said that C by N ratio is equivalent to signal to noise ratio, right? So satellite terminals may be quoted as having a negative G by T, which is below 0 dB per Kelvin. This simply means that the numerical value of GR is smaller than the numerical value of TS. That is quite obvious because in decibel scale, lower than 1, if the numerical value is lower than 1, and in decibel unit it would be less than 0. That means it will be negative value, it will show the negative value. Okay, so G by T plays an important role for the satellite communication system, right? Because if we can calculate, it will give you the same effect as that of the C by N ratio or the signal to noise ratio. Example on G by T ratio for earth station. An earth station antenna has a diameter of 30 meter, has an overall efficiency of 68%, and is used to receive a signal at 4150 MHz, that is C band. At this frequency, the system noise temperature is 79 Kelvin. When the antenna points at the satellite at an elevation angle of 28 degree, what is the earth station G by T ratio under this condition? If heavy rain causes the sky temperature to increase so that the system noise temperature rises to 88 Kelvin, what is the new G by T value? So first we have to calculate the gain for the circular aperture. So it is eta A into pi d by lambda whole square. At frequency of 4150 MHz, lambda becomes 0.0723 meter. Putting the value, you will get this converted into decibel. It becomes 60.6 dB. Now TS in decibel unit, it becomes 19 dB Kelvin. 79 was there, so 10 log 79 means 19 dB Kelvin. So G by T means 60.6 minus 19, that is 41.6 dB per Kelvin. Now if for the second part, if the temperature rises to 88 Kelvin, so under this condition the corresponding dB value will be 19.4, so G by T becomes 41.2 dB per Kelvin. Okay, so you can see that there is small change in the G by T ratio under heavy rain condition. Design of downlinks. Let me read out all these points. These are very crucial points. The design of any satellite communication is based on two objectives: meeting a minimum C by N ratio for a specified percentage of time and carrying the maximum revenue earning traffic at minimum cost. All satellite communication links are affected by rain attenuation. In the 6 by 4 gigahertz band, C band, and the effect of rain on the link is much smaller. We have discussed this thing. In 14 by 11 gigahertz, that is Ku band, and even more so the 30 uh, by 20 gigahertz, that is Ka band, rain attenuation becomes very important. Satellite links are designed to achieve reliabilities of 99.5 to 99.99% averaged over a long period of time, typically 1 year. That means the C by N ratio in the receiver will fall below the minimum permissible value for proper operation of the link for between 0.5 and 0.01% of the specified time. The link is then said to suffer an outage. C-band links can be designed to achieve 99.99% reliability because the rain attenuation rarely exceed 1 or 2 dB. The time corresponding to 0.01% of the year is 52 minutes. At this level of probability, the rain attenuation statistics are usually not stable and wide fluctuation occur from year to year. Outage occurs in heavy rain, usually in thunderstorms, and thunderstorm occurrence varies widely, and they are actually dependent on various factors. A link designed to have outage totaling 52 minutes each year may well have outages of several hours 1 year and none the next. Most Ka band links cannot be designed to achieve 99.99% reliability because rain attenuation generally exceeds 10 dB and often 20 dB for 0.01% of the time. Outage time of 0.1 to 0.5% of a year, so basically it is 8 to 40 hours, are usually tolerated in Ka band links. The allowable outage time for a link depends in part on the traffic carried. Telephone traffic needs real-time channels that are maintained for the duration of a call. So C-band and Ku band is used for voice channels with sufficient link margin that outage times are small. Internet transmission are less affected by short outages and generally do not require a real-time channel, making Ka band better suited for internet access. At the same time, Ka band has got higher bandwidth, so internet access is easier in that particular band.